All right, welcome back. So, related rates, the last part of the lesson here. We've done 3 examples. I'm going to do the last 2 in your related rates packet. Problem number D, which should be kind of an interesting, fun, hopefully kind of easy one. And then problem E, which is definitely a lot more difficult, a lot more going on in that. But it deals with a cone, it's got a trick, and once you know it, you'll always be able to get it. So, when we get there, we'll see. So related rates, last part of related rates. Here we go. So problem number D. A 5-foot ladder leaning against a wall as shown slips so that its base moves away from the wall at the rate of 2 feet per second. How fast will the top of the ladder be moving down the wall when the base is 4 feet away from the wall? And you might think, it seems logical that if it's moving 2 feet per second this way, wouldn't it be moving 2 feet per second that way? And the answer is no, because speed is distance over time, and these distances are constantly changing. So it's not going to be, even though this is moving away at a constant rate of 2 feet per second, down the wall, that rate of change will be changing. And we want to know, well, what is that rate of change? Specifically, when the base of the ladder, here's the base of the ladder, is 4 feet from the wall. So when x is 4. All right, so let's write down all of our given information. We know that t is going to be time in seconds. X is going to be distance along the floor from the base of the ladder to the wall. Y is also going to be a distance, but this is going to be the distance on the wall from the top of the ladder down to the floor along the wall. We know that the Z value here is 5. It's constant, 5 feet. The ladder is a constant 5-foot length. Now this 2 feet per second, here it is, 2 feet per second. What is that? It's the rate of change of the distance from the wall. In other words, dx dt. And that is 2 feet per second. And what are we trying to find? I'm trying to find how fast, so a rate of change, how fast, distance over time, the top of the ladder will be moving down the wall. Here's the distance on the wall. So I'm trying to find dy dt. What is that rate of change? Now, so step 1, draw a picture, name all the variables, write down all the information that's given, write down what it is we're trying to find, and now I've come to step 4, what equation relates all of these things together? And of course, I think it's pretty obvious we've got Pythagorean theorem here. There's no angles that we need to deal with, like in the previous problem. So it's just going to be nice, good old, well-behaved Pythagorean theorem. X squared plus y squared equals z squared. So now we've got the equation that relates all the variables together. We're going to differentiate that equation with respect to time. So what is the derivative with respect to time of that function? Now also notice that my z here is a 5. This is a 5. 5 squared. That's going to be a constant. The z is a 5. And when we take the derivative, z squared is 25. When we take the derivative of it, what's going to happen? All right, so as we take the derivative with respect to time of x squared is going to be 2x dx dt plus 2y dy dt equals, the derivative of 25 is 0. What is it that I'm trying to find? Dy dt, here it is. I want to get this alone by itself. So I'm going to subtract 2x dx, 2y dy dt equals negative 2x dx dt, divide by 2y, and dy dt, the rate of change of the ladder down the wall with respect to time, is, divide by 2, the 2's cancel, negative x over y dx dt. So I've got my derivative here of the formula that relates everything. This is what I'm trying to find. So now I'm going to substitute. I'm going to evaluate. What is my x value, y value, and dx dt? So let's go ahead and substitute all of those in. So dy dt, the rate of change, is negative x over y. What is the x distance? The x distance. What is the y distance? The y distance. Well, I want to note at the instant when the base of the ladder is 4 feet from the wall. That's my x value. So that's going to go in here, 4 feet. But what's the y value at that instant? At that instant, the y value, when the ladder is 4 feet from the wall, what's the y value? And again, I think we can see a nice, well-behaved Pythagorean triple here. If this is 4 and 5, this would be 3. So at the instant, the base of the ladder is 4 feet away from the wall. The top of the ladder is 3 feet up the wall. So 3 is going to go in for y. dx dt is the rate, there it is, the rate of the ladder moving away, which is going to be 2. So simplifying here, my dy dt is going to be negative 8 thirds. Negative 8 thirds is feet per second here. What's the significance of the negative part of this? The fact that it's negative. Well, remember, for velocity, this is feet per second, this is velocity here. The sign of the velocity indicates a direction. The significance here, if I go back up to my original problem, the fact that it's negative is the direction. It's going this way. It's getting closer and closer to, well, the origin, if you will. The negative, it's moving this way down the wall at 8 thirds of a foot per second when this distance is 4 feet from the base. Before that, it was moving at a different speed. After that, it's going to be moving at a different speed. But at that instant, the instantaneous rate of change, the instantaneous speed, velocity of the ladder, negative 8 thirds, moving down the wall at 8 thirds. All right. Next one, last one. Tough one. Let's take a look at this. Suppose liquid is going to be cleared of sediment by pouring it through a cone-shaped filter as shown. Assume the height of the cone is 16 inches, so the height of the entire cone is 16 inches, and the radius of the base of the cone, there it is 4 inches. The liquid is flowing out of the cone at a constant rate of 2 cubic inches per meter. How fast is the depth of the liquid decreasing when the level is 8 inches deep? So I'm dealing with a level here. Level is going to be the height. Now notice in a cone there's 2 measurements. There's the height and the radius. Nothing in here gives me anything about the radius. I want to be able to eliminate the radius in my answers. So as I take a look at this, the first thing that occurs to me, that what's going to relate all of these values together, is the volume of a cone. And the volume of a cone is 1/3 pi r squared h. But as I said, we're not given any information about the radius. We want to know the rate of change of the depth of the liquid when it's 8 inches deep. The liquid is flowing out of the cone at a constant rate. There's my dV dt. And how fast is the depth of the liquid changing? How fast is the depth of the liquid changing when the level is 8 inches deep? Well, it's 8 inches high, but what is its rate of change? dH dt. And again, I know nothing about the radius here. We need to deal with the radius. How are we going to take care of the radius here? And the thing that I want you to notice is we have, in the cone, we have 2 similar triangles. Let me use my highlighter, see if I can highlight. I've got the overall triangle. There's one triangle. And then the other triangle is this triangle right here. Now if I look at these, just these 2 triangles for a moment. Let me go over here off to the side and draw just these 2 triangles. I've got the whole triangle, and then the smaller one that's going to be inside. These are similar triangles. Well, how can we prove that? Well, from geometry. We know right angle and right angle in both of the triangles, and this angle is the same in both triangles, so by angle-angle similarity. Now this triangle I know is 16 and 4. This triangle is y, the distance, the height, and an r value. Remember, I want to get rid of, if I call this my height here, I want to be able to get rid of the radius in this problem. So I'm going to set up similar triangles here. And if we're going to use h for height here, I think we should use h for height here instead of y. If I use h, or if I plug in y and differentiate it with respect to y, I think that would be okay as well. So my similar triangles, 4 is to r, as 16 is to my height, my y. Solving for r, 16r equals 4y. r is y over 4. My height over 4. The y is my height here. This is what I'm going to use and substitute in over there. So now I'm going to rewrite the volume formula. Volume is 1/3 pi r squared h. And the h is y over 4. Oh, I'm getting confused. The h and the y really are the same thing, aren't they? The height of the cone, the amount of liquid or sediment that's left over. So I need to write that. I think I should have written that as h originally to avoid any confusion. If we call it height here, and we call it height and height and height. So my radius is going to be height over 4, and don't forget that this is squared. So simplifying this, if I simplify my formula here before I do the derivative of it, I'm going to get pi over 3 times h cubed over 4 squared is 16. Now I'm going to have a constant here. If I pull that constant out, the volume is pi over 3 times 16, 48 h cubed. All right, so now if I take the derivative with respect to time, I'm going to get the rate of change of volume over time is pi over 48 here times 3h squared dh dt. Here's my derivative. Now what was it I was trying to find? I'm trying to find how fast is the depth of the liquid decreasing. I'm trying to find dh dt. That's what I'm trying to find, the dh dt. The dv dt I know. The water is flowing out at the rate of 2 cubic inches per minute. I know dv dt. I need to solve this for dh dt. All right, so let's see. Multiply. I can do some simplifying here. Dv dt equals pi over 16 h squared dh dt. Again, I'm trying to solve for the dh dt. This is the thing that I'm trying to get alone. That's what I'm trying to find, the rate of change of the height over time. So multiply by 16, divide by pi, and divide by h squared. I'm going to get 16 over pi h squared dv dt equals dh dt. Hopefully that wasn't too crazy there, solving for dh dt. Now substituting in, I know all of the values that I want here. The height, 16 over pi times, I want to know what is the rate of change of height when the height is 8 inches deep, and the rate of change of the volume is 2 cubic inches per minute. But it's going less by 2 cubic inches. It's going down by 2 cubic inches. So can you see why I'm emphasizing that? I have to put in a negative 2 there. dH dt. Now let's bring in the calculators here to help us out. All right, so 16 divided by, open parentheses, pi times 8 squared, close parentheses. Oh, I forgot to multiply by the negative 2, haven't I? Times negative 2, and I'm getting negative 0.159 is dH dt. Now, what are the units associated with that? Oh, always a very good question. What are the units associated with that? It's a rate of change of height over time. The height we're measuring in inches, so this is going to be negative 0.159 inches per second. And again, the negative indicates that the height is getting smaller. The height is getting smaller and smaller and smaller. If we were pouring water in, and it was increasing at the rate of 2 cubic inches per second, this would be a positive number, and this would be how much the height is increasing at the instant when the height is 8 inches deep, when the water is 8 inches deep. All right, so that's our last problem with related rates. Tough unit, tough stuff here. Looking at some of these examples are kind of easy. It's always easy when the teacher does it, I know. But it can be so frustrating when you get home and you start working on it. Just remember to go through all the steps. Remember, draw a picture of what's going on, naming all the variables. Write down all the information, organize all the information, and what is it we're trying to find? Be very specific of that. It's usually some sort of rate. The something dt, in this case it was dH dt, or it could be dV dt, whatever it is. And then what's the equation that relates all of those things together? In this case it was a formula. The formula for the volume of a cone. We had an extra twist here where we had to substitute in to get rid of the radius, because we didn't know anything about radius, using similar triangles. And that's often the case with cones. Often, usually with cones, we're going to have to substitute and get rid of either the radius or get rid of the height. And then once you've got the formula, taking the derivative of it and putting all of the constants in, all the things that we know, and solving for what we don't know. All right, tough stuff, tough stuff. Good luck, and I will talk to you again soon.